Welcome back to Balvikan Bharti, and this is Avilas Sarkar. As you know, that we have just started the fluid dynamics, which is the second part of fluid mechanics. There we are discussing about the streamlined flow, a part of the kind of flow that is there in between in fluid. If it is flowing through some conduit or any contour or any pipeline or whatever you say in a closed path, then what is meant by the steady, streamline and the laminar flow. Those have start and those we have learned, and now further we have to make more understanding on this subject. Okay, so I have not rubbed this part so that we can recall it and we can further go ahead. Now few are the basic acceptance, we can say the acceptance that is needed to be fetched or to be declared before going further on this subject. So what are those? Streamline, we said, a particle moving in a path. That path itself is called the streamline, and the acceptance that has to be is there that at any point, you can say at any point, the velocity of particle, not a part of particles are same. This is the first understanding. At any point, the velocity of particles are same in a streamline. So this is in my own language I am saying. Maybe the particular language is which having in the textbook is different, but as per the understanding I am saying, at any point the velocity of particles are same in a streamline. That means if I consider this is a streamline followed by the particles which are moving in this path having same velocity at any point, because if I consider this is one cross section line, this is another cross section line, this is another cross section line. In this, now if this is the case, now this is a single line. Okay, now this is somewhat a 3D figure. Okay, if I consider this is a 3D figure, and this is again a tube inside this. Okay, so this I am saying this has some diameter. I am just considering this is. Now if it is narrowed down and it is converted into a single line, what would happen? Then after we will decide on this. But as of now, this is one tube inside that bigger tube that is following some path. So I am saying at any point of time in this path, if it is considered to be a line instead of this much of thickness path, in this point the velocity of the particle which is constantly passing through this point has to be a constant velocity. Let's say I am naming it as v1. So any particle, let's say the p1 particle, p2 particle, p3 particles, all particles is moving through this point, and initially p1 has passed through this with a velocity v1. Then when P2 will follow this same path and passing through one point should have some same velocity v1. So if it is 1, 2, 3, so any particle following this streamline path, this particular path has to be in same velocity. Let's say if it is v1, if it is v2, it is v3. So all particles following this path has to be in same velocity. So this is the meaning of this. At any point of the velocity, at any point the velocity of the particles are same in a streamline. So whichever particles following this path, in any point of time, the velocity by those particles attained has to be same. Understood? But in the second contrary, but in different point, they may differ. So this is also my language. So that means, but in different points. So that means this is one point, this is another point. In different point, they may differ. I'm not saying that will differ, but they may differ. Means V1 may not be equal to V2, may not be equal to V3. That may be different. Okay. So that depends. Okay, but it is not compulsory that V1 is equal to V2 is equal to V3. That may be is not equal to V2, not equal to V3. That may be different. Okay, maybe slight different, but may be different. Okay, so that means there are two conditions in the same point. If I consider a streamline which the particles following a particular streamline having same velocity, in different point different velocities. Okay, in different point different velocities. Okay, so these are the two acceptance to study streamline. Understood? Okay, so now if it is the case, then how will you decide velocity anywhere? So this also to be understood. As you know, in a curved path, the velocity is the tangential. If I draw a tangent, will denote its magnitude and direction. That we know because we have learned in kinematics also. If particle is moving in a curved path, at any point of time, if I draw the tangent, will show its velocity, because velocity is a vector and the direction the tangent is showing will be the direction of the vector. It will show the magnitude and the direction. So the velocity at any point of time will be denoted by the tangent at that point, the tangent at that point, the tangent at that point. Okay, this is the basic concept of velocity. So streamline, if I consider to be a curved line, then velocities at that point will be the tangent at that point, which will show its magnitude and direction together. Okay. So some now another condition is that the steady flow will only be considered or studied if the velocity of the or not the velocity, if the flow is low, means the you can say this is the steady flow is studied. Steady flow is studied when flow is low. That means there is a less flow, or you can say as I given an example of a tank with the pipe, as because the head is not much, the flow will be less through the pipeline. So the steady flow only can be considered where flow is less or low. This is the basic acceptance of streamline or steady flow. Okay, if flow is more, then automatically it will be a turbulent flow. Okay, so this is the basic acceptance of steady flow. Apart from that, there are some there are some properties, but before that I have to read what are the you can say the conditions. The consider conditions I've already said. So these are saying the path followed by any particle is the streamline, that I have already explained. The flow of the fluid is said to be steady if at any given point the velocity of each passing fluid particles remains constant. As I said, at any point of time each particle means some particle has gone through, then some is following, and if it is passing through the same point will be constant. So velocity at any point of time, the path followed by the particles has to be same. This is constant. It does not mean that the velocity at different point is same. So velocity at different point is same even if it is following the same path, means same streamline. So as I said, V1 not equal to V2, not equal to V3. So it does not mean certain sense the velocity of a particular particle may change. As I said, this V1 is equal to V2 and V3 may change. That means V1 may not equal to V2, may not equal to V3. But compulsory I cannot say this cannot be same. But that consideration definitely cannot say that V1 is equal to V2 is equal to V3. Okay, may word is there. Okay, may change and is moves from one point to other. May change means V1 can be changed to V2, which is different. That may change means there is a possibility that V1 is equal to V2 also. Okay, so this is the condition has to be understood, because this will help to solve mathematical problem also. So this has to be understood properly. So V1 definitely be V1 for all particles moving in this stream path in streamline, but V1 equal to V2 cannot said, but and that also cannot said that V1 is equal to V2. That may change means V1 may be transferred to V2 where V2 is higher than V1 or not equal to V1. Okay, so this can be said. Okay, that is at some other point the particle may have different velocities. These are the understanding when we understand the streamline flow. But every other particle which passes through the same point behaves exactly as same previous particle. So that means if as I said, if P1 passed through and P2 is coming, here the properties of P1 when it is passing through this particular point, P1, P2, P3, whatever the particle passing has to behave in the same manner. Means its velocity, its pressure, what are the flow parameters are there, that will be same. Okay, so these are the understanding. Okay, on this understanding we'll move on to some properties of streamline flow. So let me write down, then we will explain. It says in a streamline flow, no two streamlines cross each other. Why it is said? This is also a concept. Why it is said? So when a streamline flow like that, if other streamline has to flow like that, if they cross each other at the point of cross, what would happen if I want to calculate the velocity? So there are two curves. Okay, if it is crossing, let's say I am crossing that streamline 1 and streamline 2 crosses each other at point P. Okay, so if it is there, so at point P, if has to be considered velocity, then velocity will be considered by taking tangent. So this tangent is facing this way, this tangent is facing this way. So how come at same point the same particle have two different velocities and direction? That cannot be possible. If I even consider, because as a whole all particles is representing the flow through a path. So if it is a streamline flow, so every particle will be representing as a whole the flow of some mass. So at any point of time, if this is happening, they are crossing there, so the velocity at one point will get two different value and two different directions. So this cannot be possible theoretically. So this also not possible. No two streamline cross each other during the flow path, you can say. But the main understanding is that two streamline path will not cross each other. That is the main understanding. Okay, these are the properties, you can say. These are the properties. These are saying the properties of streamline flow. The second is that, so let me read out completely. In a streamline flow, no two streamlines can cross each other. If they do so, the particles of liquid at point of intersection will have two different direction of their flow. As I explained, two different direction of their flow, which will decrease the steady nature. So that means which will decrease the steady nature, because one may disturb other smooth flowing. As I said, in a steady flow, if something is restricted, so that will be a destruction to the, because if I restrict it, that will try to flow avoiding this path. So in that case, they will strike each other. If this streamline is coming to the other, will strike more, and this may cut each other. So there the turbulence will start, and that steadiness will go. Once the flow is converted into turbulence, there cannot say this is steady or unsteady. Even I cannot say it is unsteady. So once it has reached the turbulence, so this is the condition of turbulence. Understand? So this is saying that the direction of the flow which will decrease the steady nature of the fluid. So that means steady flow is converted into turbulence. So this is the condition till the flow is steady flow. Once it is gone, if this is happening, so that means the flow is not remain as a steady flow, it will be converted at a turbulence flow. The second property says, the greater is the crowding of the streamlines, yes, the greater is the crowding higher will be the velocity. What does it mean? Let me read out what they are saying. The greater the crowding of the streamlines at a place, greater is the velocity of the liquid particles at that place. So that means the greater is the crowding. So crowding, what does it mean? Let me explain it with a diagram so that you can understand it. Crowding means the change in velocity. Crowding means the change in density. So let's say my pipe is not of uniform cross section, that is having reduced cross section. Okay, this is something like that. Okay, so now a streamline is flowing there and it is moving like that. Other streamline is coming there. Due to the restriction, because the cross section here is less, here is more, so that the streamline will be more spreaded. But when it is passed through that, the distance among this will reduce. Let's say this is D1, this is D1, this is D2. So for the same two streamline, here the span is D1 is more than D2. So this is being crowded, means all the streamlines are compacted here because due to this restriction of path. So where there is a restriction, the crowding is more, here the velocity, if I say that V2, air velocity for any particular streamline I am talking about is V1, so then V2 is more than V1. This is the second property. So if there is a crowding, that means when the volume flow rate here, if I say the volume flow at the same time is flow through this, it will be compacted. That means your density is increasing here. Density is increasing. So when that density is increased due to that compactness, your velocity will increase there. Okay, and that can be understood easily because the mass flow rate, because whatever mass is flowing through that cannot be accommodated, is incompressible. So mass, whatever is crossing by this particular cross section, has to pass through this, because there is no chance of retention. This mass has to, the mass flow rate is constant. So if it is mass flow rate is constant, that means velocity into the mass is velocity into density is mass. Now if density is increasing due to the compactness, density is increasing, so that means your velocity has to be increased. That density is increased, the mass flow is same, so your density is, if it is increasing, this is compactness, so that velocity has to be increased, because velocity is nothing but the length per second, length covered per second. So time is same. In same time, if the cross section, because here cross section is more, what is your volume, that means this is volume, sorry, this is not the velocity actually, this is volume. The mass flow rate is volume into density. Now volume is what? The cross section into the velocity. So velocity here, if I have to, this volume into, this is increasing, so that means volume has to be decreased for same mass flow rate. So once the volume has to decrease, so that means cross section, when it is increased, so velocity has to decrease. Okay, so where that cross section is reducing, so this can be again related as volume is, this is, let me read out, let me write it in word, volume into density. Okay, this is mass flow rate. Okay, this mass flow rate is volume into density. Volume is again area into velocity into density. Why velocity? Velocity is nothing but the distance per time. So distance, because if this cross section, the distance, if I say this much, so the volume will be volume flow rate, basically mass flow rate is volume flow rate into density. So volume flow rate is can be calculated by the cross section and this distance traversed in per second or per unit time. So this is the volume flow rate into density. If I multiply, this will be the mass flow rate, and mass flow rate has to be constant. For the incompressible, there is no retention of mass. So as it is like that, so area into velocity into density. Now area here it is more, A1 area is more, velocity let's say V1 into density this one. This has to be same with A2 into V2 into, now this has increased due to the compactness. So this part altogether has to be reduced. Now to reduce it as a whole, if A1 is more, V1 is less. If A2 is less, V2 will be more. So that's why the velocity here will be more than velocity here. So that means more the crowded streamline, there will be an increase in velocities. Understand? So this is the second property. The third property is saying the streamline flow is possible only if the liquid velocity does not exceed limiting value. So this is another criteria, but immediately I will not go into that part because that needs some extra theory. So but as of now we just understand this. This is again the streamline flow is possible. Streamline flow is possible. This is one condition, you just keep it in mind, possible only if the liquid velocity does not cross critical velocity. So there is a velocity which is deciding whether it will be a streamline flow or a turbulence flow. If the critical velocity have some value that I am not covering here, but if the velocity of that flow below that critical value, then only we will say it is be streamline flow. This is another property. Okay. So the fourth one is the steady flow is achieved at low flow speeds, that I have already told. Steady flow is possible for low flow. As I said earlier also, it's only possible for low flow. Okay, and beyond a limiting value called the critical speed. So this is again, it is beyond what is said, critical flow beyond a limiting value, which is critical speed. Okay, now velocity is a point, because if it is constantly curvilinear path, the velocity direction is changing. So speed that at any point of time we can call it a velocity, but if it is as a whole, it is a critical speed. So that velocity at any point of time has the maximum velocity that will govern it is a streamline. So that have a specific value. So any point of time that velocity crosses, it will convert into the turbulence flow. But in a flow path, this is the speed that, apart from changing its direction, if the value also covers it crosses that value of critical speed, then also it is not a steady flow. Beyond the value of critical speed, it is not a steady flow. The flow loses steadiness and becomes turbulence. Okay, so these are the conditions. This is for a particular point, this is for a whole streamline. Anywhere it is crosses the value even, because velocity having magnitude and direction. Okay, so this thing, critical velocity, may depend on the directions also. If the direction is such that two streamlines crosses each other, then also even if the magnitude is not crossing, that may cross the critical velocity. But whereas the speed is concerned, the speed, that value itself it is covering at any point of time, it will not be a steady flow. That could be at same point of time, that may be a different point of time also. Okay, so these are the four properties of steady flow. So we'll move on to the turbulence flow. I will not move much further in the turbulence flow, because turbulence flow needs different concept and different understanding. So whatever we'll discuss on steady flow, on its different theories. So, okay, so I will touch upon the turbulence flow for understanding, and then after I'll move on to the different mathematical relations of steady flow. So thank you for now. Good night.